Imagine a planet where the entire surface shimmers like a vast, glittering jewel, where every inch is a crystal fortress forged from pure carbon. These worlds, made entirely of diamond, challenge everything we know about planets and the universe's hidden possibilities. Exploring them isn't just about uncovering cosmic curiosities. It's about expanding our understanding of the raw materials the universe is built from, and what that might mean for the future of space exploration, even human life. Stay tuned, because what you're about to see could change the way you view our cosmic neighborhood forever. Formation and composition of diamond worlds. Deep within the cosmos, some planets, or even entire worlds, could be composed predominantly of crystalline carbon, resembling gigantic, natural diamonds. Such planets are thought to form through extraordinary astrophysical processes that involve immense pressure and temperature conditions. When a planetary body's interior experiences sustained, extreme pressures, far beyond those typically encountered on Earth, carbon atoms can rearrange into robust, crystalline structures similar to those found in diamonds. These environments often involve regions of the planet where materials are compressed to such degrees that the typical carbon allotropes, like graphite, transform into solid diamond phases. This process might occur naturally during the cooling and contraction of a planet's core, or in the aftermath of colossal impacts that generate shock waves propagating through planetary material. The composition of these diamond worlds largely hinges on their initial elemental makeup. In celestial bodies originating from carbon-rich environments, such as certain types of carbonaceous chondrite asteroids or the remnants of early planetary formation, there's a higher likelihood for significant amounts of carbon to be delivered into the planet's interior. Over time, with ongoing high-pressure conditions, this carbon crystallizes into metallic or semiconducting diamond structures. Sometimes, these worlds could host layered interiors, with a shell of lighter, silicate-rich material surrounding a core made predominantly of crystalline carbon. This stratification influences not only the planet's density and gravitational field, but also potential seismic activity driven by the ongoing transformation or stabilization of the crystalline carbon layers. In some models, the unique conditions leading to diamond planet formation may involve the presence of a massive, carbon-rich protoplanetary disk around a star. If the temperature gradient within the disk allows carbon to condense directly as diamonds, especially in regions where pressure exceeds thousands of atmospheres, they could aggregate into planetary-sized bodies. These planetary diamonds are not just homogeneous balls of crystal. Rather, their formation can produce a complex, possibly layered internal structure, including a core of diamonds surrounded by transitional zones of graphite or amorphous carbon. The stability of these formations depends heavily on the planet's size. Massive planetary bodies might sustain the high internal pressures necessary to keep the carbon in the diamond phase for geological timescales. Overall, the formation and composition of diamond worlds reveal a fascinating intersection of planetary science, astrophysics, and mineralogy. Their existence challenges traditional notions of planet composition, offering a glimpse into environments where carbon's unique properties dominate large-scale planetary geology. These worlds, if discovered, could serve as natural laboratories for studying crystalline carbon under conditions impossible to replicate on Earth, shining a new light on the versatility of planetary formation processes across the universe. Physical characteristics and structural features. Planets composed predominantly of crystalline carbon, often referred to as diamond worlds, exhibit some of the most fascinating and extreme physical features in the universe. These celestial bodies are characterized by an astonishing density and hardness that surpasses many terrestrial minerals. The core of such planets is typically a massive, solid lattice of carbon atoms arranged in a diamond cubic crystal structure. This configuration results in extraordinary rigidity, creating a surface that is incredibly resistant to deformation. The entire planet, in fact, could be viewed as a massive gemstone, with a crystalline structure extending deep beneath the surface. Surface features of these worlds vary depending on their formation history and environmental conditions. Some are smooth and polished, resembling giant, polished diamonds, with minimal surface irregularities. Others display jagged, fractal-like patterns that occur naturally during planetary cooling and solidification processes. The glassy, crystalline surface often exhibits distinct facets and sharp edges due to the way the crystalline carbon crystals grow and interact. Volcanic activity, if present, tends to produce features reminiscent of volcanic diamonds or carbon-rich glass, adding even more complexity to the terrain. Crystalline carbon's high melting point and stability under intense pressure mean that erosion processes are very different from those on rocky planets. Weathering may be limited or entirely absent in some cases. The structural integrity of such planets is remarkable, allowing them to withstand intense gravitational forces without collapsing or deforming significantly. Their internal layers are likely stratified, with a crystalline mantle encasing a core of more densely packed diamond structures, or possibly a mixture of diamond and other exotic phases of carbon. The high-pressure conditions prevalent in these planets facilitate the formation of different allotropes of carbon, but diamond remains dominant because of its stability. These immense pressures and temperatures induce a lattice that is both highly symmetrical and incredibly strong, contributing to the planet's overall stability and resistance to external impacts. Despite their solidity and minimal surface erosion, the interior of diamond planets might contain regions of varying density and impurity inclusions, defects within the crystalline lattice, creating subtle variations in their physical properties. These imperfections could influence the planet's seismic activity, potentially allowing for the propagation of shock waves through the crystalline structure. The sheer strength and resilience of material makes seismic waves travel faster and more efficiently than on rocky planets. Overall, these worlds embody extreme boundary-pushing material science, encapsulating nature's ability to forge complex, stable, crystalline structures on a planetary scale. Potential environments and habitability. Planets composed predominantly of crystalline carbon, commonly known as diamond worlds, present remarkably unique environments that challenge traditional notions of habitability. Given their composition, these celestial bodies would feature a dense, ultra-hard crust capable of withstanding immense pressures. Surface conditions on such planets would depend heavily on their proximity to their parent stars. If close enough, they could harbor temperatures comparable to Earth's during the day, potentially creating transient molten or semi-molten regions. However, the overall environment tends to be intensely inhospitable due to the high thermal conductivity of diamond, which would allow heat to dissipate rapidly, preventing the buildup of surface warmth sufficient for liquid water to persist for long periods. One intriguing aspect concerns the internal geological structure of these planets. Their intense pressure could drive a thick, crystalline carbon mantle topped by a crust that resists erosion and tectonics as we understand them. This structural rigidity would likely inhibit the recycling of materials necessary for life, such as nutrient cycling through volcanic activity on Earth. Without volcanic activity or a magnetic field, which are both central to maintaining an atmosphere and shielding surface life from stellar radiation, the environment becomes even more harsh, effectively sterilizing the surface over geological timescales. Nonetheless, if subsurface layers are warm enough and insulated by layers of other volatile-rich compounds, pockets of liquid hydrocarbons, such as methane or ethane, might exist, offering potential niches for extremophile microbial life, similar in principle to some deep-sea ecosystems here. The possibility of habitability hinges on the presence of liquid solvents beyond just water, as the extreme conditions on a diamond planet tend to make water scarce or unstable on the surface. Instead, some models propose that exotic cryogenic liquids stored in subsurface reservoirs could support simple life forms under unusual chemical environments. These hypothetical ecosystems could resemble those theorized to exist on icy moons like Europa or Enceladus, where subsurface oceans are kept liquid by tidal heating or radioactive decay. On diamond planets, however, the combination of high density, high thermal conductivity, and crystalline rigidity vastly reduces the likelihood of maintaining stable liquid water environments at the surface. Still, alternate biochemistries could exploit stable pockets of hydrocarbons or other volatiles, assuming those regions remain accessible over significant durations. In summary, the environments on diamond planets are likely to be extremely hostile by Earth standards, with surface temperatures, pressures, and compositions that limit traditional forms of habitability. Yet, Their internal dynamics and the possibility of subsurface reservoirs introduce a layer of complexity that keeps the concept from being entirely dismissive. While life as we know it might struggle to thrive there, the mind-boggling diversity of planetary conditions suggests that some form of exotic habitability, likely constrained to protected niches, might still be conceivable, broadening our understanding of where life could potentially exist across the universe. Implications for astronomy and future exploration. Plans for exploring planets composed primarily of crystalline carbon present intriguing possibilities that could revolutionize our understanding of planetary formation and composition. Such worlds, often hypothetical but supported by some astrophysical models, challenge traditional notions of planetary diversity. The extreme density and reflectivity of diamond-rich planets suggest that observational techniques might need adaptation, especially in spectroscopy and direct imaging. These planets could exhibit unique spectral signatures, such as intense infrared emissions or unusual albedo patterns, due to their high reflectivity and potentially thick carbon-based crusts. Detecting such signatures would require advances in telescope sensitivity and data analysis to distinguish these objects from more common rocky or gaseous planets. In terms of geology and planetary science, the existence of planets made predominantly of crystalline carbon raises questions about their internal dynamics. Diamonds are incredibly hard, yet they also conduct heat poorly, implying that thermal evolution within such planets could differ significantly from Earth-like worlds. This would influence everything from tectonic activity to magnetic field generation. If a planet's interior is composed predominantly of crystalline carbon, models suggest it could have a stable, layered structure with a dense core, possibly affecting how it cools and interacts with its star system. Unlocking these mysteries involves not just remote sensing, but potential future missions that could analyze the planet's surface or atmosphere in greater detail. Future exploration strategies might focus on identifying candidate planets via their spectral signatures. Since diamond-rich worlds are expected to have high albedo and specific infrared emissions, telescopes like the James Webb Space Telescope or next-generation ground-based observatories could be pivotal. Additionally, their formation scenarios might involve specific conditions within protoplanetary disks, regions rich in carbon compounds, indicating that understanding planetary system chemistry is equally vital. The presence of such planets could also adjust models of planetary migration, as their extreme density and composition might influence their trajectory differently than less dense planets. The possibility of diamond planets also expands our view of potential habitats or resource reservoirs in space. While most current missions target water or metals, crystalline carbon worlds open the door to exploring novel materials with unique properties. If future technology allows extraction or utilization of these crystalline structures, it could lead to breakthroughs in space manufacturing, possibly offering near-indestructible materials for spacecraft or construction. Overall, the existence of these worlds pushes the boundaries of both observational astronomy and theoretical modeling, urging scientists to develop new tools and theories, which in turn could reshape future exploration priorities and methodologies. Usnovnoy, Rusgil 5. Planets composed primarily of crystalline carbon, often referred to as diamond worlds, challenge our traditional notions of planetary geology and composition. Such celestial bodies are theorized to form under extreme pressure and temperature conditions where carbon, existing in a solid state, crystallizes into an allotrope resembling diamonds. This transformation requires pressure levels vastly exceeding those found on Earth's surface, often present only deep within giant planets or in distant star systems. For example, certain models suggest that the interior of massive exoplanets, especially carbon planets, could have extensive layers of diamond, which may influence their physical characteristics and even their magnetic fields. These planets, if they exist, would possess remarkable density and rigidity. Diamonds are known for their unrivaled hardness, meaning that a planet composed mainly of crystallized carbon would resist deformation with exceptional resilience. Such characteristics could lead to unique geological phenomena, like highly stable crusts and limited tectonic activity compared to rocky planets like Earth. Additionally, their reflectivity and albedo would likely be extraordinary due to the crystalline nature of the material. This could affect how they absorb and reflect stellar radiation, influencing their thermal evolution and visibility from afar. In terms of formation, the conditions required for a planet of crystalline carbon to develop are thought to occur in environments where there is a high carbon-to-oxygen ratio, combined with significant heat and pressure. This might happen in certain star systems where carbon-rich material is abundant, and planetary accretion occurs in regions with sufficient energy to drive carbon into a crystalline diamond form. Some scientists hypothesize that during planet formation, carbon-rich materials could gather in the core regions, eventually crystallizing into massive diamond layers that form the planet's bulk. The possibility of these worlds existing raises questions about their atmospheres, if any, and their potential for hosting life or other interesting phenomena. Studying these diamond worlds is still largely theoretical, but advances in astronomical observation methods, such as spectroscopy and far-infrared imaging, may soon reveal more evidence of their existence. They could appear as unusually bright objects or clouds of reflective material in distant star systems. The prospect of mining or exploring such planets captivates scientists and futurists alike, as the sheer amount of carbon locked in diamond form could have implications for materials science and planetary engineering. As our understanding of planetary diversity expands, the idea of worlds made of solid crystalline carbon moves from pure speculation toward tangible scientific inquiry. Exploring the idea of worlds made entirely of diamond opens a window into the extraordinary possibilities that lie beyond our planet. We've seen how these celestial bodies, composed of crystalline carbon, challenge our understanding of planetary formation and composition. It's fascinating to think about what conditions could create such shimmering, gem-like worlds, and how their existence might influence future space exploration or even inspire new materials here on Earth. Thanks for joining me on this shimmering journey through the cosmos. If you found this as mesmerizing as First did, be sure to hit subscribe and stay tuned for more astonishing insights about the universe's most intriguing secrets. There's so much more out there waiting to be uncovered, from the mysterious depths of space to cutting-edge scientific discoveries. First can't wait to guide you through our next adventure toward the unknown. Until then, keep your curiosity shining bright.